Very good afternoon to all of you, and welcome to this first lecture for our course where we'll talk about some of the topics. We'll give you introduction to now the subject. We introduced you to the course in our last week's lecture where we mentioned what to expect in this course and what are the modalities and textbooks and so on. So today we'll get introduced to the actual topics. But before we proceed, it would be good to see if anyone has any question. Is there anyone who has some question from what we discussed last week about the course? Okay, so if there is no question, I will get started with the topic. So today we are going to introduce you to the basic concepts of databases. So first of all, need for databases, which of course we touched upon a little bit in our last week's lecture. We will also tell you a bit about the data models, and one of the models was briefly mentioned in our last lecture and also in our lab day. Then we'll talk about relational databases, design of the databases, some kind of concept about storage manager, query processing, and transaction manager. Now, one point I would like to mention, I believe that I will need to tell you the links for this slide, so which I will let you know very soon, maybe by message on MS Teams. Okay, so the need for databases, there was some introduction about that, and we asked you that in your software engineering course, for example, whether you used some sort of databases, and some of you mentioned you used MySQL or you used MongoDB and all. But of course, you could also keep most of the data that you required for your mini projects in software engineering in files as well. And database management systems are the types of software systems which are used for managing typically when the data size is pretty large and there are complex interrelationships between the various data elements. And as is mentioned as a nice short definition, a DBMS contains information about a particular enterprise, maybe say, for example, IIT Kharagpur or State Bank of India or Air India and so on. And it has got these components. It's essentially a collection of interrelated data and also a set of programs to access the data. And finally, the environment should be both convenient and efficient to use. Now, this is something I would like to clearly identify the terminology that a database management system is made up of one or more so-called databases. So these databases are these first point, collection of interrelated data, and then also a database management system other than the databases, so it could be one or more databases, and it has got supporting programs which can be used to access the data. So it is both storage of data and also it provides sufficient tools so that the data can be accessed. Now that collection of data is called a database, and the rest of the things are basically the ones that provides you some support for processing different types of languages that are supported, and these are all meant to access the data. So that would mean storing data in the first place in the databases, and then once the data is stored, later on changing them or accessing them. So that is what this set of programs is going to do. And of course, we would expect the environment to be both convenient and efficient, otherwise nobody will be using it. There are so many different database applications. Okay, now let me ask you this question, that which database applications come to your mind, the first few applications. Who can suggest some database applications? You may raise your hand and tell us which database applications you have used. Anyone has used any database application? You may raise your hand. Yeah, Aryan.
Amazon.
Very good. Yeah. So that was also mentioned last week, I believe. So it's a good application of databases. Very good. Anything else? Anybody else? So one of the yeah. Please go ahead, Jayan.
Sir, ERP and model.
ERP model. Yeah, these are also excellent examples. Now, of course, we have used different. Yeah, Varun, would you like to suggest?
Sir, Microsoft Access.
Very good. So you are talking about a database management system, Microsoft Access. Very good. So let me go back to the slides and tell you a little bit. So the terminology, these concepts should be clear in our mind. So one is, as I said, a database management system. So this Microsoft Access, then Microsoft SQL Server, Oracle, MySQL, these are all examples of database management systems. Okay. Now, if I consider one installation of say MySQL in my local machine, okay, so you have installed MySQL like we saw in the last lab class how to install MySQL in our local machines. And once you install MySQL in your local machine, you have installed that particular database management system, which mm, is an environment that ideally should be both convenient and efficient to use. Now, there you can create a database. Okay, you can create multiple databases in your own installation of MySQL. So you can create a database called MyDB. You can create a database called YourDB and so many of these. They are DB. So you can create DB1, DB2, DB3, and so on. So these are databases which are going to store some data. Now database applications. So applications are basically uh, where we have not only created a collection of data, we have also provided a user interface using which the end users will be able to access the data. Let us take this example of ERP, which is very easy for all of us to understand. If you see that, so which database management system do you think ERP uses? Anyone? You can try your luck.
SQL, sir.
SQL is not a database management system. Okay, so
MySQL.
MySQL. Okay, so one suggestion is MySQL. Anybody else? This may or may not be correct. So would everybody feel it is MySQL?
Postgres.
Okay. Second option is Postgres. Anybody else? Okay. So it actually uses Postgres. Okay. So that is the database management system. Now, inside that database management system, ERP has created several databases. Okay. So maybe there is one database for all our academic data maintenance, a database maybe for all our, say, payment related information, creating and capturing payment related information. There could be another one for, say, hall management, one other for guest house, and so on. Okay, so these are different databases, but all are within that Postgres database management system. Now you see that, do we as ERP users see the database? We do not see the database, right? Meaning that we do not know whether there is one database for academic, one for hall management, one for guest house management, or there is a single database where everything is kept. We have no idea. Okay. Also, when we talk about interacting with the ERP, as end users. So we are not also writing the program for ERP. So we are end users of ERP. So what we are doing is that we are using a database application, and that application has been developed by the ERP people for us, that is the end user. So this ERP which we are using for interacting with possibly a database that is there inside is the application. So that is what we mean by database applications here. And then you see that as we do not really know whether it is MySQL or it is Postgres or Oracle or Microsoft SQL Server or so in the as the database management system used by ERP, you see that it is really something that we did not bother as end users. Likewise, when we interact with say Facebook or we interact with say any online banking, we have no clue what kind of database management system is really being used. So we are end users of database applications, and there are people who have developed those applications for us. And even those people like the ERP, our software engineers who are working in ERP, they are using, for example, Postgres. So, but they have not written the Postgres database management system. So then there are people who actually have written the Postgres database management system. So if you work, for example, in Oracle, then you will be working on developing the Oracle database management system. And then once different versions are released, then people like those who are software developers in ERP, for example, if they wanted to use Oracle as a database management system, they will get newer and newer versions from you who is working in Oracle, and they will be having those database management systems installed, and there they will create multiple databases, one or more, for example, for, as I said, academic or hall management or guest house management. And then they will build those applications, and we as end users will be using those applications. Okay. So you see that there is a clear demarcation between who are developing the database management systems, who are developing the database applications, and then who are actually using those database applications. And of course, these databases can be very large. So the term table that some of you have heard, so we'll see later on, and I will get back to this question there about how large could the ERP database be. And databases, as you mentioned, that it touches all aspects of our lives, which is fairly easy to understand. Now, this is another example which is similar to ERP, like a university database, where there will be application program that can let people to add new students, instructors, and courses, and registration of students, and then looking at the grades and so on. Okay, and then previously, database applications used to be built directly on top of file systems, meaning where we did not have this database management system. So, as we mentioned in the last week's lecture, that one could possibly try to build the database application or the any type of such application, which maybe we should not use the term database because it is not using a database. Let us just call it end user application. So this end user application could be built or used to be built directly on file systems. But then there are several drawbacks, as we mentioned, touched upon these in the last lecture, is that there could be different file formats, and the data has to be spread over multiple files, and then it would be difficult to access the data. One has to know which data to which file to be accessed, and then we may have one file storing a part of the data, so we'll have to fetch part of the data from one file and part of it from another file, and so on. Also, it becomes tricky when there are multiple users who are accessing the same database application or the same end user application. So suppose if we are ERP users and ERP tried to use not a database management system but some file systems, then if more than one users try to access the same file, there would be some contention, and then appropriate steps are to be taken so that there is no inconsistency that creeps in. But database management systems, they inherently provide support for ensuring that in the event of multiple concurrent accesses also the data remains consistent. And several types of integrity problems can also be um, there if we use file systems instead of a database management system. For example, by integrity constant, we mean that, say, the account balance for any bank account that cannot be, say, zero, or that cannot be greater than zero. So these types of checks will get embedded in the programming logic itself. But in databases, as we'll see, that these can be defined as part of the data definition itself, and one can clearly see what are these different types of integrity constants. Now, with respect to the ERP application, can someone suggest some integrity constraint, possible integrity constraint for ERP for any part of the application that you are using? Anyone? Simple possible example of integrity.
Prerequisite check while registering for subject.
Sorry, could you please repeat?
Prerequisite check.
Excellent point. Yeah, checking for prerequisite. Okay, very good example. So that means somewhere we have to first of all mention what are the prerequisites for any course, and then once that is mentioned, when a student is registering for a course, the prerequisites have to be checked. Excellent example. Any other example? There are several examples I can think of, like, say, the slot clashes. Okay, so you see that you cannot take two courses in the same slot, or if there is a time clash. So these are examples of integrity constraints, which are easy to define in databases and not so easy if you try to build the applications directly on file systems. And there are something more interesting reasons. For example, let us say that we, uh, as faculty, at the end of the semester, okay, we upload your grades, okay, and as we upload the grades, your CGPA gets calculated. Okay, you may not be able to see that till the Senate meeting is held and so on, but it actually calculates the CGPA. Now, if I consider this step or this operation of submitting your grades, that has got two steps. So let us call it the process or the operation of grade submission, and it has got two steps in which grades get added to your information, and the second step is the CGPA gets calculated. Okay. Now, by atomicity, what we mean is that these two steps of this process, that is this updating the grade and updating the CGPA, these are two steps of the process of grade submission. So now if you see that if only the first step gets executed and second step does not get executed and the system stops there, then the problem will be your CGPA will not be consistent, will be with your grades. Okay. So we need this atomicity of operation, meaning both these steps should get carried out for successful completion of that process of grade submission. Of course, if none of them get executed, we are okay, because then your grades have not been updated and your CGP also has not been updated. Okay. So what that means is that I suppose started that process of grade submission, but in between something went wrong, my machine crashed, or the server in ERP crashed, and as a result, none of these steps could be executed. Then I will get to know that I did not successfully complete my grade submission process. Okay. But if it went in such a way that only part of it got completed and the second step did not get executed, then we are in a mess. So that is what we call atomicity of updates. So database management systems provide easy ways of supporting such atomicity, which we'll discuss in little later. And not only for one user, so there could be one other professor also submitting grade at the same time. So when your CGPA gets updated, so it should get updated in a proper way. So it should get updated by one of us first, and then that updated CGPA should itself be again updated by the other person. So just because two persons are concurrently submitting grades, there should not be any inconsistency because of this concurrent operation. So these are some of the important aspects of any such end user application which need to be handled or addressed when we are building such applications. And doing those with file systems becomes really, really tricky. Everything we have to do on our own. And that is what this database management system developers, like those who are working in Oracle or Microsoft, they are ensuring that their code for database management system, they can take care of all these issues, so that now some application developer, database application developer, like those working in ERP as software engineers, they really do not need to worry much about how to ensure all these properties of atomicity and concurrent execution and so on. And of course, security problems, that you do not want everybody, like every student, to see the grades of every other student. You can see only your own grades, right? But as faculty, we can see all of your grades. So depending on what the security requirement is, these grades can be shown to selected people. Again, we do not get to see, for example, your feedback till the results are announced. Similarly, you do not get to see or you cannot, maybe when you used to have these in-person classes, get your admit card before you submitted your feedback and so on. So these are many types of security things which are taken care of, and it's very easy to handle them in databases. So database systems, they offer solutions to the above problems. Now, based on what I discussed so far, you can see that there are essentially three levels of abstraction for the data that is maintained in a database. The physical level, that is how a record means some related information about a particular, say, subject or an object, like say for an instructor, we want to keep the instructor ID, name, department, and so on. So how it is actually stored in the physical level, because at the end of the day, the data has to be stored physically in the disk disk or any other media, so that it stays. Okay, it is not going to stay forever in the RAM. So how it is stored? So if you consider there is a file system, then physically that information for every instructor or every student has to be stored somewhere. So that is what we mean by the physical level. The logical level, which is very important, is that it is how the data is stored in the databases and their interrelationships. For example, we say that instructor is going to be a record of information about every instructor, and it will have these fields called, say, ID, which is of type, say, string, and the name, and then department name, and maybe say salary. So that is how we'll be referring to the data at the logical level. And view level, you see that when we are as end users of the ERP application, we are interacting, we see some data, which is what we are viewing, right? When you see your registration card, you are viewing that data. You have no business, or I have no business, when I see your registration card, to know where exactly the data is either stored logically in the form of these records or physically in the file system. What we are interested in is the view of the data, that if it is enough for me to see the view that, oh, here is my registration for spring 2022 semester, and it has been digitally signed by my faculty, so I can see that data, and I can, that is what I view. So that is my level of abstraction. Ideally, as a student, don't care about the logically how the data is kept or physically how the data is kept. So these are, and by physical, logical, and view level abstraction of the data. So this is just a pictorial description, and one part is good, that for the same physical and logical level abstraction of data, we can have multiple view level data. For example, you can view your data in a certain form. Say your own registration card, I can see maybe the registration information for many students together. So that is my view of the data, but the data is not stored differently for each of us. It is stored in one form in the physical level at the file system level, and at the logical level in the database, and then we are having different views of the data. So before I go to the next slide, is there any question from anybody? Then move on. So let us look at this. What is written here? Let me explain to you. So this is fairly simple to understand, that when we talk about now a database, okay. So a database typically, as we'll see, is a collection of data, and each such data is stored in the form of some schema, which we call as logical schema. So which tells us the overall structure, the logical structure of the database. So a database, let us take this example. Let us consider our ERP. So now we are talking about the ERP database. Okay, it is using Postgres, etc. We are not focusing on the database management system. So the ERP database. Now in the ERP database, and let us consider this is a single database where everything is kept. All the hall, student, academics, guest house, everything is kept. Now, in this database, how is the data organized? So data is organized in the form of what we call logical schema. Means that logically we keep some part of the data in maybe a table. Likewise, multiple such tables constitute the database. And again, now if I go back a little bit, we said that if we now have DB1 for academics, DB2 for hall management, DB3 for guest house, then all those tables that are related to academics will be organized together in DB1. All the tables which are related to hall management will be in DB2, and so on for guest house in DB3. So what we are doing is that this entire database, we are logically designing it, and these are what are called the schema of the logical schema of the databases. So it tells us that what type of information will be stored in which of the databases. Now physical schema means how these things will now get mapped to physical files, because at the end of the day the database, as I said, must be maintained in some file system. But remember this very important point, that even if I have this DB1, DB2, DB3, and say DB1 has got these three tables, say T11, T12, T13, and DB2 has two tables, T21, T22, and DB3 has say one table, T31. Now, what is important to understand is that it is not necessary that each database like DB1, DB2, DB3 will be mapped to a single file in the underlying file system. Similarly, it is not guaranteed that each of these tables, as I said, T11, T12, T13, or T1, T21, T22, or T31, these are also not necessarily mapped to physical files in the file system. So that is what is the physical structure of the database, and these different database management systems, they apply various types of optimization so that the data is appropriately stored in actual file systems in the physical schema. So what is important is that, and we of course will look into those later in our course. So we have to keep this in mind, that we initially are focusing on how to have a good design of this logical schema of the database. Okay, and later on, after say around the middle of the semester, after that we'll look into how actually this is done in how the database management system actually makes it efficient. So initial part we are more focused on designing the database, and in the second half we'll be more focused on designing the database management system. So this is what we need to consider. And the physical data independence means that even if we change the physical schema without changing the logical schema, our applications will work. For example, if today we are storing the ERP database in Postgres and tomorrow we move it to Oracle, our end user applications, we as end users, we will not be affected by that. We'll get the same type of such interface. Not only that, the ERP engineers who have this database design, say DB1, DB2, DB3, having all these 3 plus 2 plus 1, 6 tables. So they, of course, also will not need to change their this logical schema, even if they port the application from Postgres to Oracle. So that is what we mean by physical data independence. So data model. So a data model, as we understand, it's a way of modeling the data, and we are going to focus more on the first two. One is the relational model and the entity relationship data model, which is mainly for database design, which was touched upon in our last week's lecture, and also very briefly we use this term in the lab class. So we'll look into ER model and relational model, and we'll first actually talk about ER model so that we can also take up our lab classes effectively. So after this chapter 1, our next topic will be chapter 7, which talks about entity relationship data model and relational model. Now let us formally define this term tables and relations. So at this stage, we are talking about databases, and database management systems and so on. Now the databases that we are going to be using in this course, and generally the one that is most popular so far, is what is called relational databases. And relational database is very simple, that in relational databases, data is stored in the form of various tables, which is very easy to understand. Let us look at this example. We have this table which is called instructor. So each table has a name. Here this table has the name instructor, and every table has a set of columns. Here we see there are 4 columns: ID, name, department name, and salary. So that is basically the structure of the table. So even when you draw a table on a piece of paper, like we try to, not table as in furniture, but table as we want to represent some data in the form of tables. So what we have the name of the table and we have the names of the columns. And then this table actually, before you add any information in it, it is simply having that name of the table and names of the columns, which is the structure of that table or the schema of that table. And then once we add more data to it, then we are adding the rows. So in this example, we see that there is this instructor table with the 4 columns, and then we have these rows. Each row is a piece of data related to some individual, like say the first one refers to the having said the ID 22222, and then name is Einstein and department name is physics and salary is 95K and so on. So if you think of your own table in ERP, so there could be a student table, and if there is a student table, what do you think are the possible such columns in the student table? Anybody? What could be the possible columns? Yeah, go ahead.
Roll number, name, CGPA,
Okay.
semester.
Yeah, that's good. So roll number, name, CGPA, maybe your address and so on. Okay. So very good. And you said something else, right? Semester.
I mean, like department classification again, etc. Or all.
Department name. Yeah, department name is a very good example. Right. Very good. So these are the possible excellent answers. So these are different types of columns that could be there in that student table, and there you will have say these details of maybe some 13,000 students who are currently active. So that is what we could keep, and this is what is called a table. But can someone say why it is also called relational model? Okay, so let me clarify the question a little bit. So a table also is called a relation. Okay, so you see that example of tabular data in the relational model. the term table and the term relation, these are used interchangeably. Okay, so why is it called a relation? What is a relation? What is the definition of a relation from your discrete structures? Anyone? Very simple.
Mapping of two objects or some.
Yeah, that is good, but a little bit of a formal definition in terms of sets, binary relation. You all know it. Maybe
Subset
you're
of Cartesian product.
yeah, subset of Cartesian products of. So if it is a binary relation, so it is a subset of Cartesian products of two sets, which need not necessarily be distinct, right? So now each of these sets will have certain values, right? And then we are talking about this relation, which talks about the those elements which satisfy certain properties. So that subset would be defined by certain properties. So if you look at this example here, so each of these columns I can consider to be a set. So ID is a set consisting of all the possible say values. Likewise, name is a set consisting of all possible values for names, and likewise department name, there are 5 or 6 department names, and salary. So each of these is a set, and now this is a relation because it's a subset of Cartesian product of say 4 sets. Okay, and of course this subset will be derived in such a way that this value 22222 will combine only with Einstein in name and with physics and 95,000. So the element 2222, then Singh and finance and 80,000 is not a valid element of that relation. Okay. And of course, you can have only these possible, say, 12 or so such elements in that relation. So that's why you see that this is very simply a relation, and it is, in this case, it's a subset of Cartesian product of the 4 sets, and each set will have all these possible values. Okay. So the beauty of this relational model is that we store the data in the form of relations, and again the term relation and table will be used interchangeably. A little bit of other terminology is there which we will discuss as we proceed, but for the time being the term relation and table, these are going to be used interchangeably. And the beauty, as we were saying, is that the data is stored in this relational form, in this form of relations or tables, and data is also viewed, accessed, processed, all in terms of these relations or tables. So that is the beauty of this relational model. Sample relational database. So we have this first one, the instructor table or the instructor relation, which is this one. So each of this is called a table or a relation. And then here I have one more table or relation, which is having these 3 columns: department name, building, and budget, where we have this computer science, say, located in the Taylor building, and then has a budget of 100,000 and so on. So I have another table called department. So now if we have a very simple such database which now has got these 2 tables or 2 relations, so this becomes my database of 2 tables or 2 relations. So this is a sample of a very trivial relational database. So relational database is what? A relational database is a collection of relations or tables. Okay, so that means every data will be organized as one table, and the different tables or relations can have certain interrelationships. As you can see that from the first table, we see that is the department name column, and the department name column is there in the second table also. So now if we want to find out what is the name of the building where Einstein is having his office, so what we need to figure out from the first table is that, oh, where does into which department does Einstein belong? So we get from the first table that Einstein belongs to the department physics. And then I have to find out where is this physics department located. So I go to the second table. I see the physics department is located in the Watson building. So then I can then say that, oh, Einstein indeed has his office in the Watson building. So you see that these two tables, they have some linking also, so that I get to complete some part of the information by combining these two tables or these two relations, and that's why I have this as a relational database. Now, before I proceed, now let me stop and ask you. So, if you consider ERP, so ERP, and let us consider that ERP has one big database, okay, which has all the relations of tables. How many tables do you think are there in our ERP database? Any guess? Anyone wants to put forward a number? Okay, so typically, how many tables did you have in your software engineering project? Was it of the order of 4, 5, or about 10? Did anyone have more than 10 tables? So, how many do you think are there in ERP? Any wild guess?
50,
30? 100? Okay, so 100. Okay, anybody else?
50.
50 tables. Okay, any other guess? So actually, assuming again that ERP, this database is made up of all the tables that are related for managing the entire operation of IIT Kharagpur. That includes the students' academic information, the hall information, guest house information, faculty information, and anything else like your CDC and so on. So actually, it runs into close to 500 or so tables. Okay. So as you can see that it may not make sense to have a single database having 500 tables. So it might make more sense to divide it into a, a number of databases, some only having the tables related to academics, some related to guest house and so on. Because if there is little interaction between them, you may want to organize them as different databases. Okay, then each database itself does not become too large. Now, when we say that we have this table, so there is some way of defining this table so that the table is first created. And if you remember, I said that first we create the table where we give a name to the table and the names of its columns. And later on, we can add these rows to the table. So that is what is done by a data definition language. So which says that we create a table called instructor, which has got these columns, and for each column we have the type of the column. So let us not worry about what is varchar and all that. So these are different types of columns. Just as you have different types of variable in any programming language, you have different types of these columns. And when we create the table using such a syntax, and this is defining the structure of the table, so it's called a data definition language. And this actually generates a data dictionary, meaning that it tries to keep some metadata about this data. So it will create a table, and later on, suppose I enter these 12 rows in this table, the metadata that in the data dictionary will update that, oh, this table called instructor has got 12 such rows. Or if we have these 7 columns, so it will have the metadata that is in the data dictionary about the department table that will get updated to 7. So it contains some such metadata, so it has this database schema, and then some integrity constraints as we defined. For example, we need to specify that this ID will be unique in the instructor table. That means no two rows can have the same value for the ID. Likewise, for your student table, no two rows can have same value for the roll number, but the name could be repeated because two students can always have the same name, and other things like who can access that, so related to security. So these are all kept in the data dictionary. Then once we have created the structure of the table, then we have to insert the data in it, and then we have to also retrieve the data from it. So these are called data manipulation language. So we'll talk about data manipulation language, and there are these three which are pure languages. These are, we'll see later on, a few topics later, that there are three different types of such languages. One is called relational algebra, and the two are called relational calculus. One is tuple relational calculus, the other is what is called the domain relational calculus. But we are going to focus more on this commercial language, which is the structured query language, or SQL. So as we mentioned in our lab day, that you will need to start picking up SQL. Okay, so please get going on that, what is the syntax for SQL and so on, because we'll be having some lab assignments on SQL. And in our theory course on SQLs, will give you some highlights and some special subtle points about SQLs, but the basic syntax, etc., please get started with on your own. So SQL is the most widely used commercial language, and this will see that by writing SQL we can create tables. So this data definition language and data manipulation language, both are there in SQL. So in fact, this syntax that is given here, that is in SQL syntax itself. So what it does is that you can use it directly from your MySQL frontend to the MySQL backend that you install in your own machine, or in that online Oracle also you can actually write your SQL. So using that SQL, first you can create your table, or then you can add rows to the table, or you can retrieve the rows that you added from the table. So all these you will be doing using SQL. And also you can have these different programs that can have embedded SQL. So you can embed SQL in C, in Java, or any other types of languages. So so from your high-level programming languages, you can use SQL to access the data, and once you have got the data, you can process it using your high-level language. So what we'll do next is that our subject, as I said, that is to focus on the database design part, and we'll first talk about logical design, and we talked about what is meant by logical schema, and then the physical design means how it goes in and gets stored in the physical files, which will take up after the middle of the semester. So initial focus of us will be in the logical design of the database, and it's important that we have a quote unquote good design. We'll understand what is a good design, what is not so good a design, and so on, so that we can have an efficient database design. And once we have an efficient design of the database, and we'll understand what is meant by efficient, so that what we'll be able to do is that we can get started with any such application, simple application, where we can come up with the collection of tables. When you say database design, is basically is like this: what would be this collection of tables, what will be the columns in those tables, and so on. So that is what we'll try to do. So just to give you a final example of database design, if you look at this design where we have these 6 columns, okay, if you see here, we had these 4 columns here and 3 columns in the second table, of which this 1 column department name is there in both the tables. Now, instead of these 2 tables, if we came up with a design where we had all these 6 tables, 6 columns in a single table, what do you think with this design? Is there any problem with this relation? Anybody? You need not raise your hand. You can just say, see any issue with this as compared to the previous design where we had 2 tables?
Yes.
What do you see?
For example, for physics, the building name has been repeated. Like this could have been stored in a separate table and reduce the amount of space used to store the data.
Okay, okay, wonderful. So there is redundancy in data, right? That's what you mean, that every time the name physics as a department occurs with any one of these instructors, I am repeating the name of the building and the budget. So we are having a lot of redundancy in the data. That is what you mean, right?
Yes, yes.
Okay. What is the problem with that? If there is redundancy like this?
We are unnecessarily occupying more space, which we could have
Unnecessarily occupying more space. Any other issue? Anybody? let us focus on the redundancy, but other than occupying more space, is there any other issue?
Like inconsistency as well can be an issue. Maybe budget gets changed in one of the records, but
Mhm.
for a department, a budget has to be the same, as in
Right.
inconsistency is maybe introduced in the
Right.
data.
Absolutely. So that is very, very important because see the storage is very cheap, right? So we get a lot of storage free here and there. So because of the redundancy, actually we can have a situation where there is inconsistency. For example, as you said very, very correctly, that for one row here for Einstein for physics, I have this 70,000, and for this gold for physics, I might end up having a different one. So if we somehow change the budget of this department, I have to ensure I not only change in this row, I change it everywhere that physics occurs, like in this row. Okay. Similarly for the building, okay, so here I can have Watson, here also have Watson, but suppose I change in one and then I do not change in the other one, so then we are going to have a problem. Okay, is it clear? So you see that that is what I tried to mean, is that this is not a good database design as compared to this database design. So we have to figure out that first of all, what is a good design and how we ensure that we always have a good design. But there is little bit more to it, which we'll come back at a later point of time, that we need to keep in mind. So what we'll do is that there are two design approaches. One is using entity relationship model, the other is using normalization theory. So our very next topic will be about, tomorrow will be about entity relationship model. Okay, so we'll talk about that, so that we'll see how to come up with a good database design using the ER modeling approach. So that brings us to the end of chapter 1. But just for your thoughts, I'll ask you one question. Here we said that this department name physics, okay, is in say Watson building, and say I put this physics also in say Newton building here. Okay, then what is the problem? As you said just now, what was the problem? If
It's
inconsistency, right?
yeah,
But you have to also keep in mind that it is possible that the department physics is actually located in two buildings. One is Watson, the other is Newton. And Einstein actually sits in the Watson building and Gold actually sits in the Newton building of the physics department. So what is very important to understand is the underlying data, that whether a department will always be located uniquely in one building or it can be located in multiple buildings. Are you able to follow? So if we immediately say that if it is Watson, if this is Newton, it is going to be inconsistent, that need not always be correct. It will be inconsistent if a department can belong only to one building. But if a department can belong to multiple buildings, that is not inconsistent. And instead, if we actually put both of them as Watson, that would have been inconsistent. Okay. Likewise, if we see that if say this is physics Watson and physics Newton, now the budget, this is say 70,000, I make this is a 75,000. Then what will happen? It will appear that physics I have 70,000 and this physics I have made it 75,000. So there is inconsistency. But suppose this is indeed Newton building, then it could also happen that what the user wanted to mean is that the budget for the physics department located in the Watson building is 70,000, but the budget for the part of the physics department located in the Newton building is say 75,000. So there are department wise, building wise budgets, not necessarily department wise budgets. So you see that we cannot just like that without understanding the data say that this is correct or that is correct. And that is a very important point, that we have to ensure that we understand the data model correctly. Is it that a department always has a unique building, or is it that a department will always, it need not necessarily be located in a unique building? Similarly, if a department is located in multiple buildings, when you talk about the budget, is it going to be the budget for the department, or is it going to be the budget for the department for a building? So it is very important that we understand the data. And once we understand the data, how do we really know we have understood the data? We have this modeling of the data using ER model, and then we use this diagrammatically representing it as an ER diagram, and we try to model it and then show it back to the user and then ask which model is correct. Should we assign one building to every department, or I can assign multiple buildings to the same department? Is the budget going to be department wise only, or it is going to be department wise, building wise, when there are multiple buildings for the same department? So what is important is that just as you have studied use case diagrams where you draw the use cases and then show it to the actual stakeholders that, oh, so this is what is my understanding of your system, these are the different actors and these are the use cases, is it correct? Similarly here also for the data model, what we need is that we have to first represent it using ER model and then depict it as a ER diagram, entity relationship diagram. We also have to then show it back to the users that, see, this is my understanding of your data, is it correct? And once they say, oh, always we are going to have one department located in one building only, then my modeling will be something. And if they say, no, no, sometimes there could be multiple buildings, like computer science is having one main building, then an annex building, and then part of us are there in the Takshashila top floor. So there could be multiple buildings. So in that case, you see that this is not actually a bad design. And in fact, we have to ensure that for different such people, that department name, although it is the same, here in the second table for physics, it need not necessarily be only one building. So there could be multiple buildings also. So this is the point that I tried to bring out through this discussion, is that there is a need to do first this modeling of the data. If you just like the jump to a design, you will not know whether it is a correct design or not, because the design will be correct or not. That decision can be taken only based on the modeling that you are doing, and which should be something that you check it against the stakeholders' view of the data, because they know what it is. You as a software or database designer may not know whether always there will be one building or multiple buildings for the same department. So what we'll do is that we'll look at this, and after we talk about ER modeling, which is chapter 7, which we'll take up from tomorrow's lecture, then we'll talk a little bit about highlights of SQL. Once again, SQL you start picking up on your own, and after that we'll come back to the second part, which is mentioned here, normalization theory. So our next topic will be from chapter 7. Then we'll go back to chapters all these 2, 3, 4, etc. And with that, I come to the end of today's lecture. Is there any question from anybody? I am stopping the sharing, and still, if you have any questions, you are most welcome to ask. If there is no question, I am stopping the recording.